Thank you. So I should say first that I am emerite in Aix-Marseille and visiting the other university. And I didn't have enough place to type both of it. Okay? Okay, so it was not a proof. It was just a statement. Okay, so I want to prove this theorem as it is stated like that here, and as you see below, I have proved it with Pierre Fernandez and Sampaio. The point is we have to define what a Lipschitz regular, that X is Lipschitz regular at X, and that's where I define it. So in the first version, it will be that superanalytic space X is Lipschitz regular at the point X. If in an open neighborhood, it is there is a superanalytic isomorphism in an open neighborhood of Rd, which is Lipschitz. Okay. So in fact, the hypothesis of being superanalytic could be erased because maybe in the last 3 days it was it was put in the archive, a paper by Sampaio, who is one of our co-authors, to replace the existence of Lipschitz superanalytic isomorphism by Lipschitz bijection. Anyway, in this lecture today, I will only assume that we have a Lipschitz superanalytic map. Okay. So to explain the interest of this lecture, we just mentioned that in the past, Mumford proved a theorem which involves a topological property and in such a way that you have a kind of regularity. So this is a well-known theorem by Mumford, which was published in IHS. Just for the history, I remind that Mumford could not publish his theorem because people thought it was not interesting. And he met Grothendieck, and Grothendieck understood immediately that it was interesting, and he published it there. So it was because of the intervention of Grothendieck that it was published. So the reason we use superanalytic maps is this theorem by Bernick and Lipschitz. This theorem of Bernick and Lipschitz is using ideas of Gromov to have deformation into from spaces to spaces, and I translate it in an easy way. It's written like that in Bernick and Lipschitz, but as a remark that if you have a superanalytic map between two spaces, then you have a homogeneous Lipschitz differential between the tangent group. So you have this. So, if you have a reduced complex analytic space X, and X is Lipschitz regular at the point, then the tangent cone is homomorphic to a real vector space. So that's a consequence from the preceding theorem by Lipschitz. But in fact, the result of Peirce implies that the tangent cone will be a complex linear space. So I just remind the result of Peirce. The result of Peirce appeared in '67, and it was containing his thesis. I think his thesis from '65, and I must confess that I didn't know it, and it is a pre-Milner result, so something that we didn't look really clearly. I knew Peirce for other reasons, because Briscoe used some works of Peirce afterwards. And you see, if the link of C is the intersection of the cone with a small sphere centered at the vertex O, if that link is 2D minus 2 connected, where D is the dimension of the cone, the complex dimension of the cone, then C is a complex vector space. And you obtain the connectivity condition by the preceding theorem that the cone is isomorphic to a real vector space. Okay, so now we know that the tangent cone of Lipschitz regular point is a complex vector space. But there is another interesting property, that since you are Lipschitz regular, you are locally normally embedded. Normally embedded means the following thing: on X you have two metrics. Since X is embedded in some Rm, X has this metric that I give here, the infimum of the length of rectifiable path on X. And you have also the Euclidean metric, which is the restriction of the metric of Rm to X. In general, these two metrics are different, as you can see in the example of x2 equals y3. And in the case both metrics are equivalent, then the superanalytic set is called normally embedded. So the result that we are using is the fact that if you have a reduced complex analytic space which is Lipschitz regular at a point, then there is a neighborhood which is normally embedded in Cn. So the proof of this lemma is very simple, because if X is Lipschitz regular at X, then there is a Lipschitz homomorphism of a ball of an Euclidean ball with U, just given here, and you have a Lipschitz homomorphism between the ball and the ball with inner metric and the neighborhood with inner metric. And you have obviously this type of inequality, which just tell you that the two distances are equivalent. And you have also this condition here. But you know, it has been proved that Euclidean balls are normally embedded. So it means that the inner distance equals the usual distance, which is given by I wrote here absolute value, but it should be a norm. And by using the inequalities above, I obtain this inequality here. So this inequality here tells you that the inner metric on the space U is bounded by the Euclidean metric on U. So it means that U is normally embedded. So the proof of our main theorem is just a consequence of all the preceding propositions. And of the following proposition, which tells you that here I should have, I'm sorry, I glue a copy from another paper. In fact, X is a complex analytic space, and you take a point on X such that the tangent cone is a linear subspace, and I assume that the neighborhood of this point is normally embedded. Then X must be a non-singular point. So as you can understand, this proposition implies our main theorem, because if X is Lipschitz regular at a point, the tangent space is linear, and there is a neighborhood which is normally embedded. So you have these two hypotheses in this proposition, because the tangent cone is a linear subspace, and there is a neighborhood which is normally embedded. So I have just to prove the preceding proposition. So to prove the preceding proposition, I make, for instance, an orthogonal projection of Cn on the tangent space. I may suppose that the point is the origin of Cn, and then P of the point is 0. And I just noticed that the restriction of this orthogonal projection gives you a germ on X, which has the following property. On X, it is a finite complex analytic germ, because the inverse image of 0 just contains the origin. And you have this property that for a real analytic arc, then this arc and its projections are tangent at 0, because it is a tangent cone. So this projection is a ramified cover, and you look at the ramification locus, And you have a ramification locus if it is not of, if it is really ramified, means it is not of degree 1. So just remind that the multiplicity of x is just the degree d of this germ, and we assume that this degree is at least 2. So if it is 1, it just means that the point is smooth on big X. So we may assume that, and we may assume that it exists a complex analytic subset sigma, which is the ramification locus of the projection. So if it is ramification locus, you have locally a map from U1 intersection X and U2 intersection tangent cone, and outside the ramification locus, this map has degree at least 2. So now we take a unique vector V0 in outside the tangent cone of sigma, and we take the inverse image of gamma by this P. By hypothesis, I have at least two different liftings. So since V0 is not tangent to sigma, I can find a real cone like that, which does not intersect with sigma. And so I have this lifting. And this lifting, both of these liftings satisfy gamma t minus 0 equals t. And since P is a orthogonal projection on the tangent cone, the image of gamma 1 and gamma 2 are arcs which satisfies this condition here. This condition here means just that gamma 1 and gamma 2 should be outside the inverse image of, I'm sorry, this means it shouldn't be in the inverse image of this cone here. So I'm thinking why.
Can I?
Sorry?
Could I tell the argument?
Yeah, why not?
Sure. The point is, the point is that you have two arcs, right? And they have the same tangent vector, okay? But since they live quite far from the ramification locus, then the outer distance between these two arcs is smooth, and the inner distance of the is too large. Because if just to go from a point in one arc to a point in another arc, you have to go through outside this cone where they live. So it means that the arcs are just the inner distance is bigger than constant size r, and the outer distance is small because they're tangent. It contradicts to the normal embedding.
It's just what I wanted to say, but it didn't prove. Well, whatever, it's this is the inner distance between gamma I and the inverse image of sigma, and so it seems that gamma I lies outside this. Well, I don't know. I look on the maybe it's on the following page. I just have a look. So any path connecting gamma 1 and gamma 2 is the lifting of a loop based in dV0, which is not contractible in the germ at 0 I. And you are in the complement of sigma. So the length of such a path must be more than kT, because it must be more than this cone, because this cone is contractible, so it should be, so then it would be contractible. So the inner distance between these 2 points here, these 2 paths here, is at least kT. And since gamma 1 and gamma 2 have the same tangent, which is at 0, so it means V0, so the distance of gamma 1 minus gamma 2 over t tends to 0. And so we get a contradiction, because on one hand, gamma 1, the distance of gamma 1 and gamma 2 is at least kT on x. So gamma 1 minus gamma 2 divided by t is at least k. And so it cannot tend to 0. So the inner distance is bigger, strictly bigger than the outer distance. And so we get a contradiction, and we get a contradiction with the fact that the 2 distances should be the same. It's normally embedded. So that's all. So thank you very much, everybody. And well, I didn't write in all the language I knew. I'm sorry for the Vietnamese, if they are around, 2 Vietnamese. There are 2 accents I couldn't make in tech. But all the other ones don't know which accents.
Right.
Are there any questions or comments?
No Japanese.
So at the beginning you mentioned Mumford, one of Mumford's results, but there's also the Mumford result saying that the normal surface singularity is homeomorphic to relation of that part, or do you consider this as different?
No, it is in the same vein of thinking. is not the generalization, but is just to indicate that if you assume on one hand a complex structure, on the other hand you make a topological hypothesis or pseudo-topological hypothesis, then you obtain, for instance, in that case, an analytic regularity. And that's exactly what Mumford obtained. You assume on one hand complex structure, which is in that case normal surface, and then you assume topological hypothesis, which is the fact that the link is simply connected, and then you obtain a complex result, which is regularity of the surface. In fact, the motivation of Mumford was not that one. The motivation of Mumford was he was puzzled by the fact that we couldn't prove Poincare conjecture, and so he was thinking, if we cannot prove it, maybe we should look what happened in algebraic or analytic geometry. And then he found out that you don't find a counterexample to Poincare conjecture using this idea. But our motivation is a bit different. We just look at the result of Mumford. It's a type of result we are going to meet more in the theory of singularities. Is a mixture between a real structure or a weak type of structure with the complex rigidity of the problem, and then it implies some topological rigidity. But of course, it doesn't imply any analytic rigidity. In fact, in that case, it does imply analytic rigidity, but it's because we ask enough.
I remember that in his book, Miller shows that a complex algebraic set cannot be differentiable smooth at a singular point. In other words, if it represents a smooth manifold structure at a point, then it actually is a regular point. How does that compare? That cannot be used your theorem because it's very much in the same spirit, I think.
I don't know what you mean. Maybe in higher dimensions. Obviously, that's what he proved in dimension 2 for normal surfaces, that if it is locally a topological manifold, it is a manifold, complex manifold.
Differential. Yes, if you ask for differential smoothness, then it must be analytical. That's in any dimension. Hypersurface.
For Mumford or Miller?
Miller.
Miller, I see. No, it's about in the same type of vein, because but we just saw that you can only use Lipschitz.
So-called Miller's work, so can be stated as if it is infinitely regular, then it is called analytical regular.
Yes.
So you're saying
if it is Lipschitz, then it is regular. But if it is topological, it is not regular.
The differential implies foliations.
Yeah.
Differential implies foliations.
So in this sense, it's a generalization.
Yeah, in that sense, it's a generalization.
The people in geometric measure theory are very interested in results which say that a set is Lipschitz with its tangent code, whatever the definition of tangent code. In your proof, is there something that could be generalized in this direction for space which is regularly embedded in its tangent code?
What do you mean by Lipschitz equivalent to the tangent cone? There are plenty of complex sets who are not at all by Lipschitz equivalent to tangent cone.
Yes, of course. But the problem is to give conditions for that.
I see.
So I really don't know. I really don't know. But you see here in this proof we use the theory of Brill, which is another Mumford's-like result, but in a very particular case, that you have a link. If you have a link of a cone which is enough connected, it is not. It is non-singular, and it is funny if you think of it. If you have a cone and you assume that it is homeomorphic to even a vector space, then it is not so easy to prove that it is non-singular. So this result of Brill, it is very interesting. The proof of Brill, I gave the paper where Brill proved it, and the proof of Brill used a kind of, before its time, a classification of bundles. And you have a kind of notion of Versal deformation of bundles. So it is kind of funny.
Versal deformation of what? I didn't get. Versal deformation of what?
A Versal deformation of bundles.
What?
Vector bundle? Of bundle.
Oh, bundle.
Of bundles.
Bundle. Sorry.
Yeah, vector bundles. So it's a very strange proof. Maybe some young people should look at the proof, and maybe they have ideas, because these type of ideas somehow are completely lost. It came from Steenrod way of thinking of the problem. For instance, Pepe lectured several times on the obstruction theory developed by Steenrod, and I think that if you look at the paper of Brill, you might be interested.
Any other questions?
Just a remark. But it's nice that this result, the tangent cone is linear and the surface is normally bent, then it's smooth. We can look to some interesting classes of hypersurfaces which are singular and have linear tangent cone. So we conclude that they are not normally embedded, like the
Exactly.
discriminants of AK singularities, right?
Exactly.
So it's very nice. I don't know if this is known, the discriminants of the AK singularities.
But it's not surprising at cusp already is like that. So at cusp it has a linear tangent cone and it's not normally embedded. So it was more or less known, but maybe not so clearly known. The normally embedded condition is important. But of course, also the fact that the tangent cone is really a cone, is a really non-singular, reduced.
This is true.
Any other comments?
Just a remark that there is a conjecture in singularity theory, which is known as Lie conjecture, that the conjecture is the following. If you have a surface with non-isolated singularity, who is topologically regular, means that who is a manifold, then the surface is indeed a deformation of plasma. And I think that, you know, that for me it is a sort of progress in left conjecture, that I would say sort of, because here in this theorem it is needless to have an isolated singularity. I just would like to emphasize that you can, that the Mumford theorem, if you speak about normal surfaces, you need to be, the singularity need to be isolated. Here, the singularity is needless. For that, we can have, let's say, I suggest that some people will continue thinking left conjecture.
Any other questions or comments?
Just a comment along the same lines as something you said already, is that there are millions of resonance singularities whose link is a topological manifold.
Yes.
And those are automatically topological manifolds.
Yes.
Sorry, whose link is a the sphere, topological sphere.
Yes.
So those are topological manifolds, and they are certainly, as you said, non-smooth.
Yes.
So that shows that just topological, of course, is not sufficient.
Yes.
If there are no other questions or comments, we'll have a slightly longer than usual coffee break and we start again with a little more.
I have a bet that I was supposed to talk in less than half an hour. 40 minutes already.
Okay, so we start again.
Just a quick announcement. After the next talk,